In a previous video, I had analyzed what would happen if you rolled a bowling ball across level ground. The ball should travel with approximately constant velocity. And just as a reminder of what that had looked like, with constant velocity, we want the dots to be equally spaced. And we want the lengths of the arrows to be approximately the same. This is when the speed of the object isn't changing. And it had also made these graphs. There would be a straight line for the position versus time graph, which showed that it was covering an equal amount of distance in an equal time. So as you can see, these triangles are all the same and not changing in size or proportion. And the velocity would just be a constant number, so it needed to be a horizontal line in those problems. That was for a bowling ball rolling on level ground, though. And this time we're going to analyze what happens when a ball rolls down a ramp. Things are a little different. And one of the reasons why is that Earth pulls down on objects. And it can cause them to accelerate in a downward direction. But it can't cause an object to accelerate across level ground. So let's change things around. Let's put the object on a ramp now. With a ramp, we like to tilt our axes so that the x and y are aligned with the surface of the ramp. We want the x to be parallel to the surface of the ramp, and we want the y to be perpendicular to the ramp. And if we just tilt our paper a little bit, that'll allow our y to be up and our x to be to the right, but we want down the ramp to be to the right. So I'm going to draw a motion map which shows dots that we would expect to see if we took snapshots of the ball as it rolled down the ramp. And this is what we should see. We should see dots that get farther and farther apart because the ball is actually going to travel faster and faster as it heads toward the bottom of the ramp. When we started at the top and release the ball, it's at what's called rest, which means it has no velocity at that time. So I'm not going to put an arrow on that first dot. That's going to be at t equals 0. At t equals 1, the ball has moved. So naturally, it has some velocity, and I want to give it an arrow. But by t equals 2, the ball has picked up even more speed. We want to show that with the length of the arrow. And at t equals 3, as the ball is heading toward the bottom of the ramp, it's moving quite fast at that time. Now, how do we know that this is the case? Well, when we hold the ball at rest at the top of that ramp, it definitely is motionless, which tells us that it starts off with a velocity of 0. And so when we go to make our velocity graph, we want to make sure that the graph we make agrees with that observation. So start it off with no velocity at t equals 0. But then we notice that as the ball gets to the bottom, it is moving quite fast. So we want a high value for that. And this can be t equals 3, let's say. Now, since we've tilted our x-axis, we want this to be the top of the ramp. And we want our ball to start at the top of the ramp. You can see that it's at the origin here. So let's start them off at an x of 0. But later, it's at a high value. So our ball is going to end up somewhere over here as time goes on. Now, what type of curves or lines will we expect to see for these different graphs? That could be a tough question to answer if you haven't analyzed it with perhaps a camera that takes snapshots at regular intervals. But if you do, what will happen is the velocity will change in a nice, steady, straight line way. And the position will actually make a curve. And these are the graphs we expect to see for what is called accelerated motion. Acceleration means there is a change happening in the velocity with time.